All right. So thank you all for coming, and I'm very happy today to be that we're hosting Rose Yu, my new colleague at UCSD. Rose is an assistant professor at the University of California, San Diego. She's at the Computer Science and Engineering department. She focuses on research that advances machine learning techniques for um, spatial temporal data analysis. The applications she's interested in are wide ranging and go from sustainability to health to physical sciences. She's interested in physics guided AI and wants to integrate first principles with data driven models, which is extremely interesting. She's won lots of awards, including faculty research awards from Facebook, Google, Amazon, Adobe, Best Paper Awards, and so on. She's also been nominated as an MIT Rising Star in EECS. So I'm very excited about her talk. And with that, please go ahead, Rose.
Thank you, Ryan, for the invitation and the kind introduction. So today I'm happy to share some of our recent work on equivariant neural nets for learning spatial temporal dynamics. So my name is Rose Yu, and I direct the Spatial Temporal Machine Learning Lab. And this is the logo of our lab. So obviously it has a rose in it. And then if you just stare at it for a few seconds, there's also a letter S and T is hidden in this logo, stands for spatial temporal. That's our mission in the lab. So just give you a few examples of what I mean by spatial temporal dynamics. For instance, this is a video showing the temperature variation for the past 50 years from 1950 to the year 2000. So the climate models are important tools for improving our understanding of climate behavior. But climate models are extremely expensive to simulate at high resolution. So nowadays we have observation from thousands of stations across the globe. The question is, can we leverage this data combined with simulation to speed up climate models? A second example is transportation. So I spent a lot of time in Southern California, where Los Angeles is perhaps well known for its traffic jams. So in transportation, traditional methods also rely on strong modeling assumptions of drivers' behavior, and oftentimes these models are quite far away from real world data. So the video you see here is the traffic flow recorded in the city of LA from morning to night, and the bubbles represent accidents happening at different places. So given the sensor data in not only the loop detectors on the road networks, but also the cameras on the side, roadsides, can we develop better machine learning models that are better fit for real world traffic patterns, such that we can improve traffic congestion and design better control protocols. So these two examples, from climate to transportation, are examples of spatial temporal dynamics. As you can see here in different fields in climate science, transportation, public health, and many other fields in science and engineering. The common pattern is that the data contains very rich space and time information. And if we can design machine learning models that can learn from the rich space-time information, we will be able to make real-time decisions in a lot of the science and engineering problems. So compared with the traditional applications in machine learning, such as image data or text data, spatial temporal data has its own unique challenges. And because of that, in the past few years, we have been working on a framework that I called physics-guided learning to exploit the unique challenges in spatial temporal data. In physics-guided learning, we're bringing two fields together, physics and machine learning. So physics actually is a discipline that has been studying space-time information for hundreds of years. So in physics, we have first principle models and derived model-based approaches to analyze space-time patterns. So there are a lot of tools such as tensor networks, which is what I did my PhD on, differential equations, and symmetries that are fundamental to physics-based approaches. But physics-based models, because they are first principle models, they can encode domain knowledge. They're quite simple efficient, meaning they can learn with very few data points. However, physics-based models can be computationally expensive, sometimes because of numerical approximation. They also have model misspecification problem, which means the models from physics-based approaches can be quite far away from real-world data. So on the other hand, in machine learning, we rely on quite different type of approaches, which is mostly statistical inference. And we design data-driven methods to understand the dynamics in the data. So in machine learning, we have graphical models, neural networks, or deep learning, and variational Bayes to learn from huge amount of data. And machine learning methods are quite efficient in terms of computation, and they are quite flexible. So the models are very close to real world data without strong assumptions. But because machine learning is learning from data, it requires a lot of data. So it has high sample complexity, which sometimes is not a good fit for certain domain applications. Machine learning models are also notorious for being black box models, and they're very difficult to interpret. Most importantly, I would also want to argue that some of the machine learning models cannot generate physically meaningful predictions. So if we want to use machine learning models for physical sciences problems, such as traffic or climate science, it is important to ensure the predictions from the machine learning model are physically meaningful and scientifically valid. So because of that, the complementary strengths of these two fields in modeling space-time data, it's very natural to combine them together. And that's the idea behind physics-guided learning. Because we're encoding first principles in machine learning model, we're encoding inductive bias into machine learning model. Hopefully, we can improve generalization, reduce sample complexity, and eventually increase our trust in AI. So that's like the broad overview of the activities in our group. And in today's talk, I want to focus on a specific angle of physics guided learning, which is symmetries. And equivariant neural networks are symmetry encoded deep learning models. So today's talk is mostly about equivariant neural networks. Okay, so before we start talking about equivariant neural networks, let us zoom into a very specific challenge in machine learning. And this is some pictures from our paper published at L4DC, a Learning and Dynamics Control Conference this year. So this is a very interesting phenomenon of learning dynamics. What we're doing essentially is trying to fit sign functions. So we assume that the dynamics of a system follows the sine curve. So we can treat this sine curve as a time series. And the goal here is to forecast into the future. Given the past 30 timestamps, we want to forecast the next 30 timestamps from 30 to 60. So the training data is constructed in a way that the parameters that govern the dynamics, which essentially is the magnitude and the phase parameter of the sine curve, we call it theta. So the training data is sampled from the interval A and B, right, ran uniformly. And then the testing data is also sampled from the same interval A and B. So the parameters data is governing this extremely simple dynamics. And obviously the data sequences that are generated are not overlapping with each other, right? They're just drawn from the same interval A and B. So we're looking at the prediction from this model. We use a state-of-the-art deep learning model for time series forecasting, a sequence-to-sequence model. And then when we try to train this model on the data set, it is expected that the model can fit the data perfectly. And therefore, you can see the predictions in the dot line here perfectly overlaps with the ground truth. So that's not surprising. However, if we change the way we construct training and test set, right, on the right plot, where the parameter theta, which is the magnitude and phase parameter of the sine curve, is drawn from the interval A and B, but the test set is drawn from a slightly different interval B and C. And you can see here that the training data distribution in terms of parameters is different from that of the testing data. And when we train our model on this kind of data set, the deep learning model completely fails. And it actually doesn't matter what type of deep learning model we use to make predictions on this data. It's always the case that the model fails to generalize when the test data distribution is different. So this interesting phenomenon point out to the fundamental challenge in learning dynamics, which is generalization. So usually in the context of deep machine learning, when people talk about generalization, they're only talking about the distribution of the values of the data. And here, when you look at the sine curve, right, the range of the values are quite similar. So the distribution of the value itself are actually not changing from training to testing. It's only the parameters that govern the dynamics that are changing from training to testing. So it's a specific case of generalization where the change is happening in the governing dynamics itself. So in this case, deep learning also struggles, and the performance degrades significantly with test distributional shift. Okay, so that's an interesting phenomena we observe in our papers. How can we, resolve this kind of challenge? So one idea that we came up with is symmetry, because when we think about learning dynamics, when we change the data distribution, not the data distribution, but the dynamics distribution, even though the dynamics have changed from training to testing, because we're working with physical dynamics, the laws of physics do not. Right? By exploiting this fact that the laws of physics do not change, even though the dynamics are changing all the time, perhaps we can resolve this generalization issue in learning dynamics. So there is this famous theorem called Noether's theorem, which connects the conservation laws with symmetry. It's by a famous physicist Noether. She said for every symmetry, there is a corresponding conservation law. For example, the translation of symmetry corresponds to the conservation of momentum, and the time invariance corresponds to conservation of energy. So if we can build in symmetries into deep learning architectures, then we automatically satisfy the conservation laws in physical dynamics, and therefore we expect the models to be able to generalize to very different test dynamics. Another way of thinking about using symmetry in deep learning is that it is a type of inductive biases or domain knowledge that we use to constrain the machine learning models. And in this way, we can also reduce the sample complexity of learning so that the model contains the domain knowledge, only requires a few data points to learn. Because that's a high level idea. And next I'm going to give two examples of how we construct equivariant neural networks or symmetry encoded deep learning to improve generalization in learning dynamics. Okay, so this first paper is about learning symmetries in differential equations. So this is a pretty cool video about turbulence, right? And this turbulence is governed by Navier-Stokes equations, and it's extremely difficult to simulate Navier-Stokes equations at high resolution. So the goal of this paper originally was to design a deep learning model as a surrogate model that can quickly generate velocity field of turbulence. And we have done several papers on this subject, but what we realize is that the key difficulty in building deep learning surrogate models is generalization. So when we train a deep learning model on a particular type of turbulence, it often does not generalize to turbulence with very different boundary condition or initial condition. So we use symmetry in this paper to mitigate this issue. This is a work done by my PhD student and postdoc, Robin. And this is published at iClear in 2021. So a brief introduction of symmetry and group theory, right? For those who are experts in the subject, you can just bear with me for a few minutes. So in symmetry, we have a key concept called group. So a group is a set with a composition map to itself. So G, a group G with a binary operation mapped to itself, composition map to itself. We know that the identity is an element in this group. And for every element in the group, there is an inverse operation, G inverse. So an example of a group is 2D rotation, SO2 group. So this is a crude approximation of SO2. So essentially, when we rotate this object by 60 degrees, we can always rotate it back, and that's the inverse operation. With the group, we can also define the properties of the group based on invariance and equivariance. So essentially, we have invariance, which is basically the function to the group does not change. Actually, there's no G here. So a group transformation applied to the input does not change of the function value. And equivariance is a more general version of invariance, which means if I apply a group transformation to the input data x, then this group transformation will apply to the output of the function f of x. So if a function is equivariant, then when we apply a transformation to the input, it automatically applies this to the output. So let's consider a simple example. Let's say this function is the scaling function on the velocity field. So f of x, x is the field, and v is the velocity. So what this function does is to upscale the velocity field by 2. Let's consider the group of rotation, right? And the representation for this rotation, which is a matrix representation of the rotation group, can be written as a 2x2 matrix. So if we think this function f is equivariant, right, then what it means if we upscale this velocity field by 2, right, which leads to this velocity field, and then rotate it by 45 degrees and less to the velocity field on the right bottom, the bottom right corner, it is the same as we rotate this velocity field by 45 degrees first, and then upscale it by 2. And that also leads to the picture on the bottom right. So going along the routes of top and down is the same as going on the route in down and right. So if a function satisfies this type of condition, then this function is equivariant. Okay, so if we look at physical systems, right, and we want to build a deep learning model that can approximate the underlying dynamics while satisfy symmetry, we just need to look at the symmetries in physical systems itself. So in this paper, we consider 2 physical systems. The first one is the 2D heat equation, and that basically can be seen as, the heat waves propagate over time. And the second example is the 2D Navier-Stokes equation, which is a governing equation of the turbulence. So in this particular paper, we looked at the 2-dimensional turbulence. Also, this is an example of Rayleigh-Bernard convection, and it happens when the cold fluid and warm fluid interact with each other and create very intricate patterns. So for these 2 sets of differential equations, we can look at their own symmetry. Right? So in this case, by definition, a symmetry of a differential system is that if a solution is phi exists for this differential system, then the group transformed solution is also a solution. So if phi is the solution of differential system D, then for all group transformation G of phi is also a solution. And if a differential system satisfies this kind of condition, then we say the differential system has a symmetry with respect to the group G. So based on this definition, we can figure out all the symmetries included in these 2 types of systems. So for the heat equation, we can figure out that it satisfies space translation symmetry, time translation symmetry, uniform motion, etc. For Navier-Stokes equations, we know that it satisfies the symmetry in space, time translation, uniform motion, scaling, etc. And these symmetries are governed by different type of parameters listed in this table. Okay, so we know that the differential system that governs the dynamics satisfies the symmetry. The next question is, how do we encode this type of symmetries into deep learning? And that comes the idea of equivariant neural networks. So equivariant neural networks is a type of neural network that approximates equivariant functions, because we know that neural networks are universal functional approximators, but to approximate a specific type of functions that is equivariant, then this neural network becomes equivariant neural networks, right? So in general, let's say I have a function f that is equivariant, then I can construct the representations of this neural network such that the input and output mapping as a whole is equivariant. In this case, for the input and output representation, right, they are fixed, so we can't really do much about it because they come from data. But what we can do is the intermediate representations or the hidden layers in a deep neural network, as well as the activation functions at every layer. So if we carefully design the intermediate representations in the hidden layers, as well as activation functions such that they're equivariant, then we can guarantee the entire network is equivariant. So in our paper, we proved that, if with this type of layer-wise composition of equivariant layers, even with residual connections, this whole network is equivariant. So if the maps between layers are equivariant, then the entire network is equivariant. Adding skip connections or residual connections does not affect its equivariance with respect to linear actions. So that's like high-level idea. But in terms of implementation, how can we ensure equivariance? The common way of constructing equivariance, in fact, is actually through weight sharing or weight symmetry. So there's this theorem from Weiler and Sessa in 19, which gives a hint on how we can construct convolutional layers that are equivariant with respect to a particular group. So essentially, this group convolution operator, the kernel, have to satisfy group invariance under conjugation, right? So if I have a kernel in a convolutional layer, then I need to satisfy that this input, this group representation has to satisfy the conjugation, which is, the inverse operation of the group, left to multiply, and the group representation, right multiply. It will satisfy this equation. So if the input and output map satisfy this equation, then the convolution layer is G equivariant. So concretely, right, if we think about how the regular convolutional neural network achieves translation invariance, right, which is a special symmetry in the symmetry group, right, what it does is that, if I look at the symmetry of translation, right, we can basically ensure that this kernel, right, in this orange block is actually shared across translation group. So the weights, which is the edges, the black edges in this link, right? When we when we sum them up through a convolutional kernel, the weights in this orange block are exactly the same as the weights in this diagonally, the other orange block. But then the weights within the orange block are quite flexible. You can train them through backpropagation, right? But because the weights are shared from the top corner to the bottom corner, and they satisfy translation symmetry, so this way, the convolutional neural network is translation invariant. So that's the general idea of translation symmetry for convolutional neural networks through weight sharing, right? But in general, we can construct convolutional layers that are more flexible than translation invariance by construct different type of weight sharing scheme, such that the neural network itself has built-in symmetry. So that's the idea, right? Let's say if we want to generalize this idea of convolutional translation symmetry to scale symmetry, how can we achieve that? Right.
Can I ask a question? Sorry.
Sure.
Do you have any constraints on the activation functions that depend on the group?
Yeah, so like usually you wanted to construct, equivariant activation functions as well, right? So luckily, like a lot of the activation functions that we commonly use, such as ReLU, are naturally G-equivariant. So we don't need to do much about activation function in general. Sometimes if we have specific group, we need to constrain the activations to be linear, and that can be like a bottleneck in representations, but we actually didn't find any trait like sacrifice in terms of performance when we constrained activation to a specific type. But that's a great question. Hope that answered your question.
Thank you. Yes, thank you.
Mm-hmm. All right, so let's see. Okay, so now we have talked about, kind of the general idea of equivariantness, right? And then we want to generalize CNNs or convolutional nets to other kind of groups. So let's consider symmetry scaling, the symmetry group of scale. And this is a kind of mini example of how scale works in turbulence, right? We have very small eddies in coffee. And when we look at the eddies in a much larger scale on the Earth for climate science, then we need to take care of the symmetry in this kind of transformation. So standard convolution basically share weight across input by translating a kernel across input, as I showed before in the previous slides. So the kernels are shared, the weights in the translated kernel are shared across different translation groups, right? And therefore we can have translational symmetry in convolutional architecture. But for scale equivariant, we basically need to ensure that the kernel is shared not only in the translation group, but also in the scale group, the scaling group, and therefore it has a scale symmetry. So we must translate and scale the kernel across input. And this is how we construct the scale equivariant kernels, right? We're basically looking at different scale, and lambda is a different scale parameter. So a T of lambda is a scaling operator. And then when we translate along the velocity field P and Q, right, what we do is that we will scale the input velocity x by lambda, and according to the symmetry laws or the scaling laws in Navier-Stokes equation, this translation operator basically does something like scale the space by lambda and scale the time by lambda square. This comes from the symmetry laws from the Navier-Stokes equation, and we can apply this scaling operation to this convolutional kernel, and that is how we achieve the scale equivariant in convolutional neural networks. Okay, then schematically, what it does is that we upscale the velocity field by different coefficients lambda, right? By different coefficients lambda, and then naturally we'll upscale the velocity field according to the previous laws, scale the space by lambda, scale the time by lambda square, and then we use convolutional kernels to scan through the velocity field and construct and extract the features. And then we aggregate all the features from different scales together into the output features. And that's how we achieve scale equivariant in convolutional architecture for a particular velocity field. So we can do pretty much the same thing for other symmetry groups, such as rotation equivariance, and I will not explain this in detail. Rotation equivariance, uniform motion equivariance, and you can construct the kernel in such a way that is basically the same principle as translation and scaling symmetries. Okay, and then with that, I can show you how this equivariant neural networks is able to generalize to very different dynamics from training to testing. So let's say we want to forecast the velocity field of turbulence. Right? And then in this experiment, what we did is that we train our neural networks on a particular type of turbulence. And then in the test, we changed the test distribution by applying rotation or scaling or all kinds of symmetry transformation, group transformations to the test set. So to a regular deep neural network, because the data distribution have changed significantly after this kind of transformation, then the predictions will completely fail because the non-equivariant neural networks will not recognize this type of group transformation. However, for equivariant neural networks, because it automatically applies the transformation in the input to the output, so it can recognize the symmetries in the system and therefore be able to generalize from training to testing. Okay, so let's see if I change the test distribution using rotation. Right? So what you can see is this is a ground truth, right? So let's play again. So the ground truth data is rotated in a test, and the non-equivariant network completely fails because to itself, it's a very different type of data distribution. It cannot forecast correctly. So we're forecasting the velocity field of a turbulence. And similarly for uniform motion, right, when we translate the test data by a certain amount, then the equivariant neural network will recognize the change in the training distribution and being able to detect that and react accordingly. Similarly for scaling, when we apply this to a real-world data set of ocean current forecasting, where we take the previous velocity fields and trying to forecast the future velocity field of an ocean currents, what we see is that if we look at the ResNet, which is a non-equivariant deep learning for forecasting velocity field, when we upscale the test data by different coefficients, right, the non-equivariant model ResNet, the error explodes when we upscale the test set. However, when we look at the equivariant counterpart, the scale equivariant neural network, we can see that the forecasting error stays relatively stable when we change the tested distribution by different factors. So this left plot is the forecasting RMSE, which only measures the forecasting accuracy in terms of point-wise velocity fields error. And the right plot is a physics-based metric called energy spectrum error. So this measures the physical consistency of the forecasts. It looks at different energy cascade in the turbulence of the forecast turbulence. So what we can see is that this model that is built in to be equivariant also generates physically meaningful forecasts. So the physical error in terms of forecast also does not change that much when we change the test data distribution by different factors. In contrast, the ResNet or the non-equivariant models will have exploding errors when we change the test distribution. So this kind of gives you an idea of how we can leverage symmetry in deep learning such that the deep learning models are robust in test distribution and being able to generalize within a group transformation. The next example I want to talk about is more related to real world data. And that's the idea in the field of transportation. So in transportation, a critical task is trajectory prediction, right? It's a pretty complicated task because in the physical science domain, such as the differential equations that we talked about, right? We only need to care about the dynamics that governs the equation, the dynamical equation that govern the equation that govern the dynamics, and that's about it. But in kind of transportation domain like this, right, we not only need to take care of the physical system, the physics underneath it, but we also need to take care of human psychology, which is much more complicated than physical sciences. So the people drive in a very chaotic fashion. Even though it does look like fluids, there's a lot of randomness in transportation when we try to forecast the future trajectories of how cars are going. And in this paper, we designed a equivariant neural network that is rotational equivariant, but also can take care of this kind of complication in human psychology. And this is work done by my postdoc and grad students, Leo. So when we look at real world traffic, there's very intricate symmetries built in our human decision making. So when we look at cars, there are many particle systems, right? But when we make decisions, for example, when we drive in North Hemisphere, right, we know how to make a right turn. However, when we move to South Hemisphere, let's say Australia, we also know how to make a right turn, which means that there is internal symmetry in how we make decisions when we drive. And the key insight in this paper is that when we build models to forecast the trajectories of cars, perhaps we can exploit such symmetry to predict the trajectory of cars on the road. So if this model is successful, then this model should be able to distinguish left turn from right turn and give consistent predictions at intersections when the intersections are rotated with different orientation, right? Showing this figure. So we think there's rotation symmetry in traffic or in many particle systems. So we expect our model to give consistent predictions with different orientation. So we start with a type of convolutional architecture called continuous convolution. So different from the discrete convolution in image field, continuous convolution is designed for point clouds. Or rather, it is related to graph neural networks, but we don't have to get into that today. So discrete convolution, right, as I said, is that with the grid field, the grid or the graph, they're fixed. And we're looking at, convolution kind of around the neighborhood, and the underlying grid is not changing over time. So this discrete convolution. Similarly, if it's an image, then we can think of the underlying, skeleton is a grid, and the grid does not change when we change the features on the grid. But for cars or for point clouds, right, in this example, the cars are moving around. So there is no fixed reference frame underneath the trajectories. So when we do convolution or when we do like aggregation around a neighborhood, we need to take care of this kind of time evolving reference frame. So, and that's the idea behind continuous convolution. So in this case, xi and xj represent the position, a 2D position of each of the car, right? Xi is a i's car, j is a j's car. And the feature of j is basically, the angles and the velocity and angles for this particular car. So you can think of them as features of this position, right? And then continuous convolution is built on the idea that when we look at, the feature representation of a particular car I, for example, we need to aggregate all the features around the i's car. So we're looking at all the neighbors j. So for all the j's in this neighborhood of I, we're going to aggregate all the nodes, right, all the features according to where they are. So we're looking at all the i's in this cycle, in the circle, within the circle, and then multiply by the features of that node. And this is continuous convolution. So the continuous convolution itself is not our paper, but it was used predominantly in point cloud, estimation and used for trajectory prediction. But continuous convolution itself is not rotation equivariant. So the key contribution of this paper is to design a type of continuous convolutional architecture such that it is rotation equivariant. So if we think about this particular equation itself, right, we can think about the feature representations. So our data is point cloud. So for point cloud, we have points, xi, which is the position in the space. In this case, is the xy coordinate of the point. And on top of the point, we have features on the points. So the features, when we look at, let's say the velocity, the angle, right? These can be represented as S2, as a function, as a vector field over the point cloud. So for every point, we have some features which are vector field on the points. Okay. And then the input and output in our model are basically the velocity field and the angles of different cars. So we wanted to map the SO2 features into the general linear group using a rotation group, a continuous rotation group. So that is basically the representation map that we want to learn using our equivariant neural network. So because we're working in an SO2 group, when we map the hidden features from the SO2 group, and that becomes the hidden features. This is the functional space on top of the SO2 group. So the hidden features in our neural network are actual functions on the cycle. So because where input is SO2, right? Then when we learn the hidden representation using a deep neural network, then the hidden representation or hidden features becomes functions on the circle. So this is the different layers of representation in our deep neural network. Visually, it represents this kind of functions on the circle, right? So we have a circle, which is the input and SO2, and then we have values on top of the circle, and that becomes, the hidden features in our deep neural network. Okay, so in order to design our equivariant continuous convolution, right, or ECHO, we use the principle of constructing equivariant convolutional architecture. So this comes from the previous theorem of Weiler and Sisa, which says that when we construct the convolution G equivariant convnets, we need to ensure the group action is satisfy the invariance under conjugation condition. So we need to find the input and output map under the rotation group. So in this case, to impose this kind of constraints, right, we propose an efficient weight sharing swing by basically constraining the weights on this kernel to satisfy different kind of conditions. For instance, we're looking at SO2, right? So we discretize the polar coordinate into slices of pizza slices. And in this case, we wanted to ensure that the weights are shared along the orbit. So that's in this way for a particular angle theta, and then for a particular radius alpha, we want to make sure that the weights are shared along this orbit. Okay, and then the only tricky part is in the center, and there's a bullseye. So for bullseye, we need to constrain the weights to satisfy this type of circular pattern. So the weights are constrained to be constrained by a stabilizer. And that is basically the weights on the center point of the kernel. So the rest is quite similar, where the matrices, once we constrain the weights to be shared along the orbit, and then the stabilizer is constrained in the center, then the rest of the weights are freely trainable. You can train them with standard backpropagation techniques in deep learning. Okay, so because our hidden features are functions on a circle, right? And then we can basically think of this kernel as a tori. So it becomes features on this kind of, tori. The feature of the tori, when you cut it open, it becomes, each of the pieces become the weights become the weights of the kernel. So by cutting open the torus and the features along the red and the orange line, we can identify the operation with matrix multiplication, which is essentially showing on the left-hand side. Okay, so this is how we construct the continuous convolutional kernel such that it satisfies the rotation equivariance. And then with this kind of special convolutional architecture, we can build a deep learning model that can help us forecast the trajectories of cars. So in this case, we have the trajectories as the input, and these are SO2 input, right? Trajectories of different cars, the input representation. And then we use a fully connected layer to map the input trajectories into some hidden representations. And then we encode the map information. So this top one is a map information, and the bottom one is a multi-agent interactions, and the third one is a single agent behavior. So we separate three types of information using three different continuous convolutional models. And each of the model is our model, a equivariant continuous convolution. And then we concatenate the intermediate representations using a fully connected layer, and that give us, function on the circle, right, for each of the little cars. And then we again use a continuous convolution to aggregate all the features in the hidden layer, and then that will generate the predictions, which is the delta in x, which is the velocity. So that's the velocity in the positions for the cars. And then we can calculate the future position by adding the velocity to the previous position. And we repeat the process by several layers. So this is the deep neural network with several layers of continuous convolution. So in general, this part of the input encode the past trajectories of cars. We encode, map information, multi-agent information, and single agent behavior with three separate continuous convolutional layer. And then this part of the model decode the future, which generate the future forecast of the trajectories given the encoded hidden features. For the encoder and the decoder, we use continuous convolution to ensure the entire neural network is rotation equivariant. So that basically constructs the whole model, and that's our model, also known as ECHO. Okay, so let's look at the practical performance of this deep learning model. We compared our model with several state-of-the-art baselines. So these are standard baselines. Constant velocity is a very simple baseline. We just predict the cars to have constant velocity. Therefore, the velocity is not changing. We can just forecast their future trajectories. And nearest neighbor uses the nearest neighbor of the particular car using the neighbor information to forecast the velocity of a particular car. LSTM is a sequence model for trajectory forecasting. The main competitor in our model is continuous convolution. So this is the previous method for forecasting trajectories, but it is not rotation equivariant. And we have two variations of our model. Rho 1 equivariant echo is only on the input feature representation. It's a Rho 1 representation. And regular representation is we also use the hidden representations in our deep neural network. So we looked at two data sets, two benchmark data sets in trajectory prediction. Nargoverse is an autonomous vehicle trajectory prediction benchmark. TrajectoryNet is another pedestrian trajectory benchmark data set. So we're looking at error, so absolute distance error. This is in terms of the deviation from the ground truth. The lower, the better. We can see that for 1 second to up 3 seconds, our model achieves the lowest error in terms of forecasting performance for both data sets, right? And then we also included a state-of-the-art model VectorNet from Waymo, from Google Waymo. So VectorNet actually have a similar performance as ours, but it has much more parameters in the model. Another thing about VectorNet is it only generates prediction for a single car at once, where our model can predict for multiple cars simultaneously. So they're not really a direct comparison, or include in their model anyways. So the most important thing is here, where we look at the number of parameters we need to train this model. We can see that compared with continuous convolution, right? A Rho 1 echo only uses 20% of the parameters of the original model. So because we're encoding symmetry as an inductive bias, so we need actually a much agile model, a smaller model to train on this task and being able to even outperform in terms of forecasting. Another interesting result we saw is the learning speed. So this is the validation set versus number of training examples. As I mentioned, if we use symmetry as an inductive bias, we can significantly reduce the number of examples, the sample complexity of the learning. So we can see that the Rho 1 echo in the orange line, it converges really fast using 3,000 examples, whereas the non-equivariant neural network requires a lot more examples to be able to learn well. So this demonstrates another benefit of sample complexity when we incorporate symmetries in deep learning. Okay, so these are the two examples of equivariant neural networks in learning spatial temporal dynamics. To conclude, I talked about designing equivariant neural networks for learning complex spatial dynamics. I mentioned an example of differential equations. By using equivariant neural networks, we enable automatic generalization within a group transformation. We also evaluated on point cloud data using a continuous rotation equivariant neural network, and we observe significant improvement in sample complexity of learning. In terms of future work, I think a natural idea is to extend this to probabilistic settings where we need to quantify the uncertainty in the prediction. So there is a separate line of research on probabilistic symmetry that we're currently exploring. So that could be a future work. You can look at the code and the data in these 2 papers I talked about on my website, or follow me on Twitter, where I sometimes publish the most recent updates from our group. And I want to acknowledge the support from various funding agencies for supporting this work. Thank you very much.
Thank you, Rose. That was really cool.
Thank you.